Greetings and welcome to this presentation on inverter types and considerations. I'm Amy Shear, curriculum developer and instructor here at SEI. Let's get started by taking a look at our learning objectives for this particular unit. We have several sections in this unit, and by the time you get through all of them, you should be able to describe the most common inverter topologies that you'll be encountering in the PV industry, as well as their associated grounding configurations. You also should be able to evaluate different inverter choices and system configurations, meaning the different types of inverters such as string inverters, central inverters, and microinverters and DC to DC converters, which also fall under the category of module level power electronics. So we'll take a look at those different types of inverters and how they fit into different system configurations. And you should also be able to evaluate the impact of different inverter choices on PV system electrical design and configuration. So we have a couple of case studies at the end where we'll take a look at the benefits and the downsides to different types of inverters in different specific system configurations. So let's take a look at the different inverter topologies that you will encounter in PV systems. There's two main types, and the first one we're going to look at is transformerless inverters, or also known as TL inverters. And just like they sound, these inverters do not use any type of isolation transformer as part of their system functionality. So they might also be referred to as non-isolated inverters because there is no galvanic isolation between the AC and the DC sides. So the DC circuit on these inverters is ungrounded when the inverters are not operating. And when they are operating, the DC circuits are considered functionally grounded. And so there's a DC reference to ground through the electronics inside the inverter. And we'll talk more about grounding specifically in the next unit, but we kind of can't talk about these different inverter types without talking also about the grounding configuration, because that's kind of what separates these two different types of inverter topologies, is the way that they're grounded within a system. So transformerless inverters, TL inverters, non-isolated inverters, those are all the same, and those are probably the most common inverter that you're going to come across currently in systems being installed today. And this has kind of been the case for about the last 10 years or so. Before that, we were mostly dealing with transformer-based inverters. And so just like it sounds, these inverters contain a transformer that isolates the AC and the DC sides from each other. So you might also hear those referred to as isolated inverters. And this type of system has one functionally grounded DC conductor. And so usually that's going to be the DC positive or the DC negative conductor. And that's going to be grounded through the inverter in a ground fault, through a ground fault protection device. And usually on these inverters, that's going to be some type of a fuse, usually a low current rated fuse like 1 or 2 or 5 amps. And so that's going to be the means of connection to ground from the DC side on these transformer-based inverters. Both types of inverters have to have equipment grounding, and so that's really important to keep in mind. Again, we'll talk more about grounding in the next unit. So I want to talk a little bit about solid grounding versus functional grounding. So solidly grounded per the NEC definition means that something is connected to ground without any resistor or impedance device, which is in this case would be like a fuse. So it's a solid, direct physical connection to ground. And so an example would be like the main bonding jumper in a main service panel. That's a connection between the grounded conductor and the equipment grounding conductor at the service. And there's other examples you can see in this photo on the right, upper right side here. We have a green ground screw that's bonding the grounded conductor to the grounded enclosure. And then we also can see in the bottom photo, we have a common or shared bus bar for grounded conductors and ground. So these would be considered solid connections because they're bolted, physical, hard connections. So one thing to keep in mind, the DC side of pretty much every PV system you're going to encounter is not considered solidly grounded, is not have a solid connection to ground. Non-isolated and transformerless type inverters have an electronic connection internal as they're part of their internal circuitry that monitors for ground faults, and that's definitely not solid. And then isolated or transformer-based inverters have a ground fault protection device, which is usually consists of a fuse connection between one current carrying conductor on the DC side and ground, and that is also not solid. The fuse can blow or it can be removed, and that's not a solid connection. 690.2 in the National Electrical Code gives us the definition of grounded functionally or functionally grounded, and that refers to a system that has an electrical ground reference for operational purposes that is not solidly grounded. Remember, the functionally grounded systems on transformerless inverters are functionally grounded when those inverters are operating, but when they are not operated, those DC conductors are not grounded. There's an informational note in 690.47 that also states most PV systems are functionally grounded systems rather than solidly grounded systems as defined in this code. So just keep that in mind as you're working through these systems. It can be kind of confusing to keep all the terminology straight, and they kind of in 2017 made this sort of distinction so that solidly grounded systems and functionally grounded systems are two distinct types of systems, and most of what we'll be dealing with are going to be functionally grounded systems. So that's the end of part 1. Take a break and come back for part 2 when you're ready. We'll be talking about DC system grounding in a little bit more detail.